Hello, class. Welcome to the Stat 312, Chapter 5, Part 2 video. To start off with, we're going to talk about the inferences of variances when we are working with two independent samples. So far in the previous Chapter 5 video, we are focusing on the differences of population means. So now we may want to consider what happens if two population variances differ. So one may want to determine if the constant variance assumption for a pooled t-test is responsible. And while we don't normally concern ourselves with this too much in Chapter 5, it is something we should be aware of. And I can tell you that I'm more than likely at some point on one of your exams going to ask you to complete a pooled two-sample t-test and then have you check the assumption that for equal variances. Another thing we may be considered about is that one may be primarily interested in making inferences on the variances in such situations of quality control. And so in that situation, we really focus on the one-sided hypothesis test. And what we mean by quality control experiments is if you're thinking of an assembly line, ideally you want all of your parts coming off the assembly line to be about the same thing. So for example, something that might be a bit more relatable to you is think about the number of chips in a bag of chips. Ideally, the number of chips in a bag should be equivalent across all bags. And so we want to, in other words, have a consistent amount of chips. Well, when we use the term consistent, in general, we're talking about the variability. Now, if we are trying to implement a new method, we obviously are going to want the variability to be the same or better yet, less than it was previously. So for us, in order to test variances, when we want to try to compare the differences between two variances, say two sample variances, S1 squared minus S2 squared, this doesn't have a very simple distribution. So instead, we actually are going to use the F distribution, and we can use the ratio of F equal to S1 squared over S2 squared. Now, one thing I do want to talk about real quick about like how do we determine which sample to use for 1 and 2. Generally, when we're using means, we tend to label the first one to be the first one we read about. In inferences, when we're doing one-sided hypothesis and two-sided, regardless of which comes first, always put the larger hypothesis on top. The reason is if the population variance 1 is greater than the population variance 2, then our corresponding F statistic with using our sample variances will give us an F distribution or give us an F statistic that is greater than 1. And this just keeps everything consistent for us, and also makes understanding two-sided hypothesis easier if we keep it as that one-sided with the larger variance on top. So for as assumptions for this, we do need to have two independent random samples of size n1 and n2, and they must be coming from a normally distributed population. The hypothesis test of interest for us will be the null hypothesis that assumes the two population variances remain the same versus the alternative where one population variance is greater than the second population variance. And again, this is focused on the one-sided hypothesis test. Again, the statistic we'll use will be our two sample variances over each other. Make sure you put the larger sample variance over the smaller one. And we could compare this to the F distribution with the degrees of freedom n minus 1, comma n minus, or excuse me, n1 minus 1, comma n2 minus 2. In the F distribution, if we take a look at that table, which we can do right now since we have referenced it, we can notice that there are degrees of freedom across the x-axis and the y-axis, the numerator and the denominator. Numerator on top, denominator on bottom. So the degrees of freedom that correspond to the larger standard deviation or larger sample variance is the numerator, and the denominator is the smaller. This does go on for several pages. It is dependent on not only the degrees of freedom, but of course also the alpha size, which you can find at the very top. So this case, it's the alpha of being 0.1, scroll down 0.05, and so on and so forth. So talking about how we determine our test, now that we've taken a brief look at our table, our rejection region for this is that we will reject H0 and infer that our null hypothesis is true if F, our test statistic, is greater than F alpha with the degrees of freedom of n1 minus 1, comma, n2 minus 1. And this critical value, F alpha, is directly from the table that we just showed you. And again, remember, alpha is at the top of the page, n1 minus 1 is the column, and n2 minus 1 is the row. So let's take a quick example of this. And I apologize, I keep accidentally writing. All right, so a quality control guru wants to fill weights of peanut bags to be more consistent. Remember that word consistent implies variability. From the current process, 11 bags were sampled and had a standard deviation of 0.282. After installing a new control device on the fill machine, another 9 bags were sampled, and this independent sample had a standard deviation of 0.130. Is there sufficient evidence at the 10% level to infer that the new control increased population consistency? Now, one thing I do want to note, because as I've said before multiple times, that consistency implies that we're talking about variability. When we have an increase in consistency, that means we have a decrease in the variability. So now we can start by setting up our problem. First, step 1, we can state our null and our alternative hypothesis. Our null hypothesis is going to assume that the old population variance and the new population variance are going to remain the same. For the alternative hypothesis, we are assuming that the old variance is going to be larger than the new variance, meaning it is less consistent. Step 2, we can calculate our test statistic. Which in this case is 0.282 over 0.130. And remember, we were given standard deviations, but the problem calls for variances. So we're going to need to square them. And this will give us an F statistic of 4.7. Now we are able to move on to step 3, which is that we will reject the null hypothesis if our test statistic is greater than F alpha, which in this case is 10%, with degrees of freedom 11 minus 1, comma 9 minus 1, which would be equivalent to the F being 10, comma 8. So now we can find our critical value. Pulling up our F table, we had a 10% level, And here we are right here. Numerator degrees of freedom was 10. Denominator degrees of freedom was 8. Meet, and our critical value will be 2.54. Going back to our slides. So we're comparing against 2.54 to our critical value of 4.7. Clearly, this is greater than 2.54, so this implies that we will be able to reject the null hypothesis. So this means that at 10% significance level, the null hypothesis was rejected. There is sufficient evidence to infer the new control increased population consistency, aka it decreased the variance. I want to remind you guys that the second part of our conclusion talks about the alternative hypothesis. As I stated in slide 18, or excuse me, not slide 18, going up one more, slide 17, that we may want to determine if the constant variance assumption for the pooled two-sample t-test is reasonable. This is the test we're going to use. We want, ideally in that case, for the population variances to be equal. So in that situation, ideally, we fail to reject the null hypothesis. What tends to happen, though, is that because students are looking to have equal variances, they tend to forget themselves and they write the line as there is sufficient evidence that the population variances are equivalent. Remember, we never accept the null hypothesis. We fail to reject it, or we cannot fail to reject it. So please make sure that you're always talking about the alternative hypothesis in your conclusion. It is a part that a lot of students get wrong, and I'd rather it not happen to you. So that brings us to the end of our discussion on variances. Let's now move on to talk about our inferences of proportions. As we've seen in our pattern so far, when we were talking about one sample inferences, we talked about means, then variances, then proportions. We're following the same pattern for our two sample cases. For the rest of this lecture, we're going to primarily focus on inferences on two proportions, and then at the very end of this lecture, we'll wrap it up and try to summarize everything we've been talking about so far. So for inferences on proportions, we may need to have a two-sample problem with an inherent variable being recorded as two values, such as success, failure, true, false, defect, non-defective, yes, no. This is unlike the preceding situations involving means and variances, where the inherent variable is being recorded as numericals, such as weight. So in chapter 4, we had one population where it was the population proportion of some success. Now we're going to have this binary population where P1 is the probability of success in population 1 and P2 is the probability of success in population 2. So we're going to say that Given samples of size N1 and N2, we want to make an inference on the difference between the two populations, or P1 minus P2. So if we recall, when we were dealing with a single population, our estimate for P was P hat, which was equal to Y over N, where Y was the number of successes and N was our sample size. Now, in a very similar fashion, when we have two populations, we'll estimate P1 and P2 with P1 hat and P2 hat, where P1 hat is Y1 over N1 and P2 hat is Y2 over N2. Y1 is the number of successes in sample 1, and N1 is the sample size for sample 1. And in similar fashion, P2 hat, Y2 is the number of successes for sample 2, and N2 is the sample size for sample 2. So now comes to the all-important statistics. So the statistic P1 hat minus P2 hat has a mean of P1 minus P2 and a variance of P1 multiplied by 1 minus P1 all over N1 plus P2 multiplied by the quantity of 1 minus P2 all over N2. And it is approximately normal if N1 and N2 are largest. So therefore, by standardizing, developing a z-score of the quantity of P1 hat minus P2 hat and quantity minus the quantity of P1 minus P2 all over the square root of our variance, then it will follow approximately the standard normal distribution. This is not our test statistic. But we're getting there. All we were trying to establish in that slide was how the statistic of P1 hat minus P2 hat follows the normal distribution, and by using z-scores we can convert it to the standard normal distribution, which we care about. But now we can actually focus on the hypothesis testing itself. So for us, our null hypothesis will be P1 equals P2. You may alternatively see it as P1 minus P2 equal to 0. Either option is fine. It is simply up to you. And that is that we are testing that the population proportions are equal. So under this null hypothesis, we're going to pool the samples to estimate the common population proportion. And so for that, we're actually going to use this statistic of P bar, which is actually equivalent to N1 P1 hat plus N2 multiplied by P2 hat all over N1 plus N2. So if we simplify this, this actually becomes Y1 plus Y2 over N1 plus N2. Or in other words, the total number of successes over the total sample size. The idea behind this is similar to when we were doing the pooled variance statistic for making inferences on two population means. So using this statistic, we are able to calculate our test statistic, which is z equal to p1 hat minus p2 hat minus our hypothesized value, which in general is going to be 0, divided by the square root of p bar 1 minus p bar multiplied by the quantity of 1 over n1 plus 1 over n2. And we do compare this to the standard normal distribution, just like we do when we were comparing one population proportion. Now, as we've gone through the theory, let's now take a look at an example. So in a test of reliability of products produced by two machines, machine A produced 6 defective parts in a run of 300, while machine B produced 10 defective parts in a run of 200. Is there sufficient evidence at the 10% level to infer a difference in the reliability of our two machines? So step 1, state our hypothesis. Our null hypothesis will assume that everything has remained the same. And because we're talking about machine A and machine B, I'm going to go ahead and label it as PA and PB. And our alternative, we assume that some sort of change occurred, but we are unsure of the exact change. Step 2, we'll calculate our test statistic. We know that PA hat is 6 over 300, which will be equivalent to 0.02. PB hat is 10 over 200, which is equivalent to 5% or 0.5. And our P bar is 6 plus 10 over 300 plus 200, which is 16 over 500, which will equal 0.032 or 3.2%. Now we have all the pieces that we need in order to calculate our test statistic. So z will be equal to 0.02 minus 0.05 minus 0 all over the square root of 0.032, 0.968, which is 1 minus 0.032, multiplied by the quantity of 1 over 300 plus 1 over 200. This will give us our test statistic of negative 1.87. Excellent. Now we can move on to making our decision and stating our conclusion. So for our decision, we will reject our null hypothesis if the absolute value of z is greater than z alpha over 2. Our alpha in this case was 10%, so that means alpha over 2 is 0.05. If we pull up our z table, we want to get as close to 0.05 as possible. Which is exactly in between 1.64 and 1.65. So as usual, we split the difference and this would become 1.645. So comparing the absolute value of negative 1.87, which equals 1.87, it is indeed greater than 1.645. So therefore, we will reject our null hypothesis. This leads us to step 4, stating our conclusion. So we will say, At the 10% significance level, if I cannot skip words, that would be important. So at the 10% significance level, the null hypothesis is rejected. There is sufficient evidence to infer a difference in machine reliability. And as always, that first line should state whether we reject or fail to reject the null hypothesis. And then the second statement should be we either have sufficient evidence or insufficient evidence of our alternative hypothesis. And at this point, that's all I really wanted to talk about in concerns with comparing two population proportions. I do want to do a real quick practice exercise talking about whether or not we are going to be looking at dependent samples or independent samples. I'm going to skip over this demonstration as we are working online, but instead I'm going to read a few scenarios and try to determine whether these are dependent samples or independent samples. So for our first situation, for each car in a sample of cars, stopping distance when going 50 miles an hour was recorded on wet pavement and then again on dry pavement. As we are comparing the same car going into two different situations, to me, that is going to have a natural pairing, so therefore this is going to be a dependent sample. Our next one says that test scores from public and private schools were compared by sampling multiple schools of each type. There's no natural pairing that I'm aware of in this situation, so I'm going to call this a two independent sample situation. Next, to study inflation, an economist obtained the price of a room with a king bed in 2016 and 2017 for 100 hotels. In this situation, I'm assuming that we are comparing the same 100 hotels both in 2016 and 2017. So in that case, there would be a natural comparison of comparing a single hotel's price in 2016 and 2017, and then comparing all 100 hotels before and after. So to me, this would be a dependent sample. For our fourth situation, a sample of patients who are randomly split into control and experimental groups. The control received the established treatment and the other group received the new treatment. This to me would be a situation of two independent samples, as there is no natural pairing that would occur between the control and experimental groups. Finally, Mylan Pharmaceuticals sampled batches of a drug produced in two of its plants to see if purity differed across locations. In this case, without having more information, I'm going to assume it's two independent samples. But if we are comparing the same drug, or I should say, if we're comparing the exact same drug in two different locations, then it would be two independent samples. If we were comparing, say, the same three drugs in one location and then comparing the same three drugs at a different location, then I would say it was a dependent sample because we were comparing drug to drug. But as we are not given that information and it says a drug, not multiple drugs, I'm going to go with that we are comparing a single drug in two different locations, and therefore it would be two independent samples. Okay, so one important thing that I want to do to wrap up this lecture video is to talk about where your knowledge starts and stops and kind of synthesize everything we've been talking about so far in this class. So one thing, our focus so far has been on obtaining the general idea behind inferences for two populations, being either dependent versus independent sampling and inferences on means versus variances versus proportions. We did not cover everything in chapter 5 in this video. For example, we didn't cover confidence intervals for two proportions, confidence intervals for two different variances, and the two other inferences for the means. That would have made this video much longer, and I really don't want to take up more of your time than I necessarily have to, because at this point you generally have a pretty good understanding of confidence intervals, and essentially you know when a situation for the confidence interval is required for, because generally the question says construct a 90% confidence interval. So it's more of just knowing the formula than needing to know any of the theory behind it. And any situation in this course that you're presented with where you would need to construct a confidence interval for two variances or two proportions, you would be able to easily look up the formula. So I felt that I would focus more on the theory than just throwing every single formula at you, as I did not think that was worth your time, something that you could easily teach yourself. Next, what we did focus on in this lecture and in our previous lecture was so that you would have a general understanding of statistics, and that if you were ever in the situation where you would have to have a statistical consult with a statistician, you would have an understanding of what they're saying. Many large companies and government agencies do employ statisticians, and research universities have statistical consulting centers. And it is important that if you're passing your research off to them to perform statistical analysis, that you're able to explain really what you are looking for them to do. And also, when they give you their results, you're having an understanding of what your results actually mean. Because in statistics, math is the first part, understanding is the second part, and in fact, the most important part. A final thing to say is, as we discussed earlier, not all samples are independent. Section 5.52 explains how to compare proportions using paired samples. We aren't covering this in detail either, but there are certainly situations where this occurs, but it is not something I will test you on. But you should be aware that they do in fact exist. Okay, so the last thing I want to do is I'm actually going to make a bit of a diagram for you guys to try to, like I said, synthesize everything we've done so far. So I'm going to pull up a blank page, and you may want to either go to the back page of your notes or get a blank piece of paper. All right, so let's get started drawing our nice tree diagram to really synthesize all the information we've learned in this course so far. So the first thing I'm going to do is try to split my screen in half horizontally. And this is going to separate our knowledge from chapter 4 and chapter 5. So the first big difference between chapter 4 and chapter 5 was the number of samples we were working with. In chapter 4, we focused on the situation where we had one sample, and this chapter 5, we focused on the situation where we had two samples. In chapter 4, we focused on two different numerical types. Variable types. The situation where we had numerical data and then when we had that binary data or that yes, no. When we had the yes, no situation, that's when we were talking about proportions. And we discussed constructing a confidence interval for P and a hypothesis test for P. When we were working with our numerical data, we briefly talked about hypothesis test for inferences, but we really focused on inferences in regard, oops, sorry about that, in regards to means. And by that, we did focus on the confidence interval for mu, the prediction interval, and the hypothesis test. You may recall, and this might be helpful to you to write down the formulas. For the confidence interval for mu, that was y bar plus or minus t alpha over 2 multiplied by the square root of the variance divided by the square root of n, or sorry, the standard deviation divided by the square root of n, or the square root of the variance divided by n, depending on what you're given. We were given the prediction interval and then the hypothesis test. We had the test statistic of t equals our sample mean minus our hypothesized value all over s divided by the square root of n, and we compared it to the t distribution with degrees of freedom n minus 1. I'm not going to spend a whole lot of time going through and writing all of the formulas, but you may find it helpful to do so. So this is really what we focused on for Chapter 4. Now for Chapter 5, which we've been talking about the past 2 weeks, once again, we were really focused on the situation where we had 2 samples. And for us, our next big focus was whether we were working with dependent samples or 2 independent samples. In the situation where we had the two dependent samples, we primarily focused on the numerical variable type mu d. And for that, we looked at, and I apologize, I was about to sneeze. We focused on doing a confidence interval and a hypothesis test when we had the 2 dependent samples. We briefly talked about that the proportion for 2 dependent samples exists, but we didn't go through it in depthly, and it's not something I'm going to test you on. Primarily, we really focus on 2 independent samples. And from there, we talked about the numerical variable type when we had the means and when we had variances. We talked about when we were dealing with means, we talked about how to do both a confidence interval and a hypothesis test. For variances, we just discussed how to do a hypothesis test, and we primarily focused on how to do a one-sided hypothesis test. As I said before, though, we didn't just focus on the numerical variable type. We also talked about that binary situation for our yes-no, and we talked about how to do a hypothesis test when we are comparing P1 and P2. And so that's pretty much a nice synthesis of everything we've covered so far in this course. It is a lot of information. I do understand that. And pretty much, in my opinion, the hardest part about chapters 4 and 5 is reading a scenario and determining what are we looking at? Is it one sample, two sample? What type of variables are we looking at? And then going from there. So you may find this little tree diagram very helpful to you. You may want to make it bigger than I have and include all the formulas, and you can use those to solve problems on your homeworks and exams. All right, so that's it for this lecture video. As always, if you have questions, please shoot me an email. Have a good night.